right, geometry students, back by popular demand. You asked for it, you wanted it, and here it is. More on conditional statements. Yeah. All right. In this lesson, we're going to be learning more about conditional statements and more types of conditional statements. So far, we learned what a conditional statement was. It has a hypothesis, it has a conclusion, if, then, all of that. We also learned that we can take a conditional statement and flip around the hypothesis and conclusion and find the converse of that conditional statement. As long as a Venn diagram showing the cases of the hypothesis and the cases of the conclusion are exactly the same, then we can flip around and the converse of a statement will also be true. That's what we've learned so far. In this lesson, we're going to learn two more types of things that we can do with conditional statements. And the first thing we're going to learn in this lesson is a tool that we're going to use to get to one of our new types of conditional statements or new transformations of conditional statements, and that is a negation. Okay, so a negation is a tool we're going to be using. It's when we take a statement and we just change it so it's the opposite of a statement. It is 85 degrees outside today. The negation of that statement would be, it is not 85 degrees outside today. So all you do is you put the word not into a statement in the correct place, and you negate the original statement to say the opposite. That's a negation. Now, here's the first transformation of a conditional statement that's new in this lesson, the inverse of a statement, and it uses the negation. The inverse is a statement formed when the hypothesis and conclusion of an original statement are negated. Remember, the converse is when they're switched. The inverse is when they are negated. All right, so let's think about a conditional statement. If it is 95 degrees outside today, I will wear shorts. The negation would be, if it is not 95 degrees outside today, I will not wear shorts. You see how I just changed the hypothesis and conclusion to include the word not? So that's our first type of conditional statement for this lesson. Now, we've already learned about the converse. Remember, so our statement, if P then Q, the converse sounds like inverse, but it's very different. The converse, we flip around the hypothesis and conclusion. So our statement becomes, if Q, then P. Now, here's the inverse. So we're going to learn a new symbol. The inverse is, if not P. We use this symbol here to show that we're talking about the negated statement, not. If not P, then not Q. That's the inverse of a statement. Now, a couple other relationships we need to talk about. Logically equivalent statements are two related conditional statements that have the same truth value. They're related because they're transformations of each other somehow, okay? And here's the big relationship you should know. The converse and the inverse of a conditional statement have the same truth value. Okay, and what that means is they're logically equivalent statements. They're two related statements. They're related because they're transformations of the same statement, and they have the same truth value. Let's go back to my statement. If it is 95 degrees outside, then I will wear shorts. The converse of that is, I will wear shorts. If I am wearing shorts, then it is 95 degrees outside. I'm not sure that that's true because I might wear shorts if it's 90. I might wear shorts if it's 80. So even though the original conditional statement is true, the converse is not necessarily true. You'll find me wearing shorts when it's 87 out, and then you'll say, oh, that's a counterexample. All right, now let's think about the inverse of the statement. The inverse was, if it is not 95 degrees outside, I will not wear shorts. Well, again, I don't know if that's true because I might wear shorts when it's 80 or 85. So that has the same truth value as the converse. You'll find that's always true. The inverse and the converse always have the same truth value because they do similar things to the statement. All right, the other thing that we need to mention, another relationship, If you find the inverse of a conditional statement twice, you'll arrive back at the original statement. And that next relationship is true of our next transformation. The second transformation we're going to learn in this lesson is the contrapositive. We form a contrapositive by exchanging and negating both the hypothesis and conclusion. So this would be, in my statement, if it is 95 degrees outside, then I will wear shorts. Well, I have to both exchange, like I would with the converse, and negate. So that one would become, if I am not wearing shorts, then it is not 95 degrees outside. If I am not wearing shorts, then it is not 95 degrees outside. Let's think about that one for a second. So if I am not wearing shorts, and I always wear shorts when it's hot outside, that means that it must be pretty cool outside. Then it is not 95 degrees outside. That one probably has a truth value. I mean, aside from absurd situations where all my other clothes are dirty and all I have to wear are shorts or something, that one is very, very likely to be true. So the contrapositive of a statement is found by switching the hypothesis and conclusion and negating both of them. If not Q, then not P. Okay, let's take a look at some example problems because that's where we're going to actually find this is useful. So let's see, letter A says state the hypothesis and conclusion of this statement and then its converse. Okay, so what we're going to do, we're going to shrink this down and I'm going to make my font a little smaller so we can fit on the page here. Let's see, state the hypothesis and conclusion. So for letter A, the hypothesis is going to be everything after if but before the comma. A polygon is regular. That's the hypothesis, okay? The conclusion is it is convex. It is convex. That's the conclusion. Now, the contrapositive of that statement is if a polygon, notice it says it in the conclusion. I have to identify what it is, though, as a pronoun. I have to identify what it refers to in my hypothesis. So I'm changing it to a polygon. If a polygon is convex, then it is regular. Letter B asks me to evaluate the truth value related to the statement and its converse. So if a polygon is regular, then it is convex. So the statement is true because there's no such thing as a regular polygon that's concave. Some of the angles would have to be different, and it can't be regular unless it's equiangular and equilateral. It could be it could be concave and equilateral, but it can't be equiangular if only some of the angles are such that there's a diagonal that passes outside. So the first statement is true. The converse, though, let's see, if a polygon is convex, then it is regular. Well, I can think of all sorts of convex polygons that aren't regular. They don't have to have equilateral sides or be equiangular to be convex. So the converse is not true. The converse is false. Okay? And again, I can think of lots of counterexamples to prove that polygons that are convex don't necessarily have to be regular. All right, letter C. Identify the hypothesis and conclusion of the statement below, then write the negation of each. So Durrell buys juice. That's the hypothesis. And then he buys pretzels is the conclusion. Okay? The negation of this would be Durrell does not buy juice. And then he does not buy pretzels. All right. I'm just going to take one space away here. There we go. Let me spell pretzels correctly, too, just so no one can complain. All right, there we go. Letter D. write the inverse of the statement below. If the statement is true, is the statement true? Is the inverse true? Okay, so for two lines that are cut by a transversal, if the lines are parallel, then the same side interior angles, those aren't usually congruent angles. Those are usually supplementary angles. So that's interesting. So anyway, write the inverse of the statement below. So for two lines cut by a transversal, I'm just going to leave that out for now. That should be a part of it because it's necessary to make the statement work. So if two lines cut by a transversal, there we go, are not parallel, then the same side interior angles are not congruent. Okay, so that would be the statement's inverse. I negated both the hypothesis and the conclusion. Now let's think about whether these are true. The first statement is false because for two lines that are cut by a transversal, the same side interior angles are supplementary, not congruent. So they're only congruent if the transversal is perpendicular, and it doesn't say anything about that. So for any diagonal transversal, this is false. What about the inverse? If two lines cut by a transversal are not parallel, then the same side interior angles are not congruent. This is an excellent exercise in geometric reasoning. So if I can find one situation where two lines cut by a transversal are not parallel, but the same side interior angles are congruent, then I can prove that this is false. Okay, so what I need to prove is that the same side interior angles can be congruent. And here I have two lines cut by a transversal. I don't think I'm going to accomplish this by making this line any lower, right? Because if I tried to make this go down lower, my angle's becoming more and more obtuse. And this is an acute angle. I'm never going to make it congruent. But what if this transversal was on, let's see, I bet you I could do it just by making this line different. Because, okay, so I can go from being, well, let me think about this for a second. Yeah, so I can go from having an obtuse angle to having a right angle, okay, and then having an acute angle, and then an extremely acute angle. So somewhere in there had to be the angle that was congruent to this angle. So it is possible for me to make two non-parallel lines cut by a transversal with congruent angles. It's just really hard to figure it out from drawing it this way. But there's definitely a way to do it to make congruent angles on the insides here. So therefore, the inverse is also false because there is at least one counterexample of the inverse. All right, letter E. Letter E is determine a contrapositive of the statement. If two angles are complementary, then the sum of their measures is 90 degrees. Now I have to flip the hypothesis and conclusion and negate them. So it becomes if the sum of two angle measures is not 90 degrees, then they are not complementary. That's the contrapositive. Now, it didn't ask me to evaluate the truth value of this. Let me just fix, there we go. But if I think about this, if the sum of two angle measures is not 90 degrees and they're not complementary, well, that just makes sense. That is a true statement because that's the definition of what complementary angles are. And then finally, determine the converse of the solution to problem E. What do you notice? Okay, the converse of that means I have to flip around the hypothesis and the conclusion. If two angles are not complementary, then they are not, then let's see, then the sum of their measures is not 90 degrees. What do I notice? This is the inverse of the original statement. So if I take the converse of the contrapositive, I have the inverse of the original statement. And